Let's take a look at the level structure of CO3. First, carbon has 4 valence electron. The oxygen has 6 valence electron times 3 atoms. That's 18. 18 plus 4 will give me 22 valence electrons. The minus 2 here means that it has gained 2 extra electrons. That's plus 2. That will give me 24 valence electrons. We have a video on how to draw level structure, so you can check it out for better understanding. So carbon is the central atom, and we have oxygen atoms as terminals. So we have 3 oxygen atoms. I've used up 6 electrons here. So if we subtract 6 from the total, we're going to have 18 valence electrons. Okay, so we assign them now to the terminal atoms. Okay, so I've assigned 18 valence electrons now in total. So subtracting 18 from this, 18 minus 18, we get 0. So this should be the level structure for CO3 2 minus. Of course, the minus sign, we have to put this in a braces like this and put a 2 minus up here. That is an ion. Do you understand? Now there's a problem here. What's the problem? The problem is that the oxygen atoms are obeying the octet too, and atoms have to obey the octet. Octet says that every atom should have a total of 8 valence electrons in the outermost shell, although there are some atoms are exemptions. We talked about that in the previous videos. So if you look at carbon, carbon only has 6 valence electrons. That's 2, 2, 3, that's 6. So it needs 1 and 2 more electrons to complete its octet configuration. What can carbon do? Take a look at this lone pair. Look at this oxygen over here. This oxygen is what we call an electron-rich atom. This also is electron-rich. This also is electron-rich. So what carbon will simply do is to take one of the lone pairs of the electron-rich oxygen and use it to form a new bond, something like this. So watch. Take for example, imagine I have something like this. This valence electron, that's this lone pair, these 2 lone pairs in brown color, is used by the oxygen to form a new bond. Okay, so what will be formed? Let me rub this off so as to create space. Okay, so what will be formed? Something like this. We have our carbon, we have our oxygen, our lone pairs. This oxygen, I've used 1 lone pair to form an extra bond, which is this bond over here in brown. Because this oxygen will therefore have 2 lone pairs remaining. You understand that? So this is a possible structure or a possible level structure for CO3 2 minus. Of course, we still have to put this in a kind of square braces like this. Okay, and put your charge 2 minus. Now another way we can draw this structure is by taking, instead of taking a lone pair from this top oxygen, you can take it from this oxygen instead, where this lone pair becomes a shared pair and comes over here. Okay, so how is that going to look like? It's looks something like this. We have our carbon, we have oxygen up here, we have down here, we have our lone pairs. Now one of the lone pairs have been used to form an extra bond, isn't it? Which leaves this oxygen with just 2 lone pairs of electrons. Okay, so this is a possible structure for CO2. The possible structure for CO2. What else can we do? We can also assume, okay, so of me taking electrons of these 2 oxygen atoms by the right, I can take from this one by the left. So I can take one of the lone pairs here and need to form a bond here. Okay, there are 3 different possible scenarios here. Okay, so what's that going to give me? Something like this. And finally, one of the lone pairs here was used to form a new bond, so we'll have a double bond here, leaving this oxygen with just 2 lone pairs of electrons, just 2 lone pairs of electrons. So you can see there are 3 different possible combinations or 3 different ways of drawing the level structure of CO3 2 minus. So each of these structures you see, each of this structure you see here is called a resonance structure. So that means that CO3 2 minus shows what? It shows resonance. Now, what is this double bond? This double bond you see here, whenever you see a single bond is a kind of bond called sigma bond. So single bonds are called sigma bond. Okay, so when you see just a single bond like this, okay, it's called what? A sigma bond. When you see a double bond, one of them is sigma, look at the one in white, and the second one is a other kind of bond they call pi bond. They also have a kind of bond called pi bonds. So it's called pi bonds. Okay, the symbol for sigma, the symbol for this is the symbol for sigma bond, and for pi bond, the symbol for pi bond is this. So if I say, when I write this, I mean pi bond, and when you see this, I mean what? Sigma bond. So double bonds, when you see double bond, one of them is sigma and one of them is pi. Okay, now there's something interesting about sigma and pi bonds. The one thing you should know is this: sigma bonds, and write this over here. Sigma bonds contains electrons called sigma electrons. Okay, and these electrons are localized electrons. While pi bonds contain a kind of electron or kind of electrons called pi electrons. Okay, so pi bonds contain pi electrons, and pi electrons are delocalized. When you say something is localized, it means it belongs to a particular region. Localized electron means that it belongs to a particular thing. Do you understand? It belongs to a particular region. So when I say localized electron, I mean it belongs to a particular carbon or particular atom. Okay? While the localized electrons, they don't belong to a particular, just like the opposite of localized, they don't belong to a particular atom. They can move around in a molecule. Are you getting that? So let's come back to my diagram over here. Look at this sigma bonds. Let me use green to color them. Look at these bonds here. These bonds, they are all sigma bonds, and sigma bonds are they contain localized electrons, meaning that the electrons here belong to just what? Just carbon and oxygen. That's why it's called localized. The electrons here belong to just this oxygen and this carbon. The electrons here belong to this carbon and this oxygen. You understand how they call sigma electrons or sigma bonds? But now for pi bonds, look at this pi bond here in brown. They are not localized. That means that they don't just belong to these two atoms. They can move around. They are called delocalized electrons. So they can move around in a molecule, within a molecule. That concept of pi electrons moving around the molecule is what we call resonance. If you take a look at this, you can see initially the pi bond was here. Now it is here. And now it is here. What can you say? You can see that the pi electrons in the pi bonds are moving around within the molecule. Okay, that concept is called what? Is called resonance. And the kind of structure that arises from resonance are called resonance structure, or you can call it canonical structures. Are you getting that? So within these three structures, we put an arrow sign, a double-headed arrow sign, to show that these structures are resonance structures. So each of them are the structure or the acceptable structure for CO3 to minus. But the fact here is that the best way to understand this is that each of them, none of them is actually the real structure for CO3. They are only contributing to a particular structure called the resonance hybrid. The resonance hybrid. What do I mean by resonance hybrid? Now, these structures are called resonance structures, right? Now, each of them contributes to a general structure called the resonance hybrid. Let me give you the structure. It looks something like this. Now, what does this tell us? It tells us that these dot lines tell us that the pi electrons, which is this pi bond over here in white or fade brown, it's telling us that the pi electrons are moving randomly within the molecule. They don't actually belong to a particular set of atoms. They belong to the entire atom of the molecule. Do you understand? But that's what it's all about. That's what resonance is all about. So this here, this structure is called, we call this structure the resonance hybrid. So each of the resonance structures are contributing to the resonance hybrid. They can all contribute equally, or one may contribute one more than the other. So let's assume that we call this the resonance structure A, B, and C. So A, B, and C can contribute equally to resonance hybrid G. Okay? Or in some cases, the resonance structure A might contribute most to the resonance hybrid. So if A contributes most to the resonance hybrid, it means that the acceptable structure for CO3 is what? Is this resonance structure A. If B contributes mostly to the resonance hybrid, it means that B is a acceptable structure for CO3 2 minus. Another molecule, a very interesting molecule that shows resonance, is ozone. So if I'm to draw this, do something like this. Here we have our 3 oxygen atoms. Okay, the central atom has just one lone pair of electron, and terminal have a stable octet configuration. You can go ahead and attempt to draw the other structure of O3. If you look at this very, you see that oxygen here, the 2 terminal oxygen atoms, they have a stable octet, but the central oxygen atom does not have a stable octet. So what can you do? As I said in the previous example, you can take electrons from the electron-rich terminal atoms. Draw the lone pairs here on terminal atom and be used to form a new bond, making it something like this. This center oxygen now have the stable octet. This is 2, 2, 2, 3, that's 8. Other way that this can happen is by taking the lone pair from here. Okay, so what are going to form? You're going to form something like this. So what do you call these 2 structures? They are called resonance structure. You have to put an arrow sign, double-headed arrow sign, show these are resonance structures. Now, none of them is actually the acceptable structure for O3. So they are only just contributing to a structure called the resonance hybrid, which looks something like this. If you use your eyes and kind of take a peek at this, you see that if you look at this pi electron moves from here over to this point, isn't it? Over to this point, that would form this, and this move over to this point, that would form this, and so on and so forth. So the back and forth movement. You understand? So this here, this one over here is called the resonance hybrid. The resonance hybrid. So the resonance structures contribute to the resonance hybrid. If this is resonance structure A and resonance structure B, A and B can contribute evenly to the resonance hybrid. If they contribute evenly, it means that any of the structures are acceptable structures for O3. But if A contributes more, it means that A is more acceptable than B. The question now is how do we know which of them is acceptable and which of them contributes more to the resonance hybrid? We calculate something called the formal charge. The formal charge. The next video will talk more about the formal charge.